A-Level Mechanics, Circular Motion 2. We're going to have a look at what happens if the angular speed is not necessarily constant. And in particular, we'll look at some problems when the motion is in a vertical circle. So let's consider what happens when we have variable speed circular motion. Up until now, we have considered objects rotating about an axis with constant angular speed. However, often the speed can vary, but we'll still assume that the radius is constant. For example, consider a pendulum. As the pendulum swings down towards the centre, it speeds up, and as it moves away from the centre, it slows down again until it stops. Its speed is continually varying. In this case, there are no forces except gravity acting in the direction of the motion. So we can use conservation of energy to calculate its speed at any time. Let's see what happens to the acceleration of a particle during circular motion. Consider a particle P rotating about a point O. We've seen that the tangential acceleration, AT, is r theta double dot. Also, even if the angular speed is not constant, it turns out the radial acceleration is still v squared over r, which we can write as r omega squared or r theta dot squared. Let's look at an example. Example 1. A pendulum of mass 0.8 kilograms has a light rod of length 1.2 meters and swings up to an angle of 60 degrees to the vertical. In part 1, we have to find the tension in the rod when the angle to the vertical is 60 degrees. Well, to solve this, we have to draw a diagram and mark in the forces. First of all, we've got the weight, which is 0.8 g, where g is equal to 9.8. We've then got the tension in the rod, which we can call T. And since the pendulum has no velocity, the only acceleration is tangential to the circle. So, resolving radially, we have the angle between the weight and the rod is 60 degrees. So, T is equal to 0.8 g cosine 60 degrees. Now, the cosine of 60 is a half, so we've got 0.8 times 9.8 times a half, which is 3.92. And so the tension in the rod is 3.92. Now in part 2, we're asked to find the tension in the rod when the angle to the vertical is 0 degrees. Now of course we need a diagram. Now we're going to work out the speed of the particle using energy. So for the potential energy we need a zero height. So we'll take the lowest point of the pendulum as being zero height. Now we need to find the height of the pendulum weight when it's at 60 degrees to the horizontal. So we need to draw a horizontal line from B to the vertical AC. Now if we look at the triangle ABD, we can see that AD is equal to 1.2 times the cosine of 60. So CD is equal to 1.2 minus 1.2 times cosine 60, and cosine 60 is a half. So that's 1.2 take away 0.6, which is equal to 0.6 meters. Now we can use the conservation of energy to find the final velocity. The final energy is equal to the initial energy. Now the final potential energy is 0 and the final kinetic energy is a half mv squared. The initial potential energy is mgh and the kinetic energy is 0. Now we can cancel the m's and we can double all the way through. So that gives us v squared equals 2gh, where g is 9.8 and we've worked out that h is 0.6. So that's 2 times 9.8 times 0.6, which is 11.76. Now if we resolve vertically up at C using F equals ma, then we have a weight of 0.8 g downwards, and we have a tension which we can call S going up. So that gives us S minus 0.8g is equal to 0.8a, where a is v squared over r. So we have S is equal to 0.8 times 9.8 plus 0.8 times v squared over r, which is 11.76 over 1.2, and that works out to be 15.68 newtons. And so the tension in the rod is 15.68 newtons. Let's look at another example. Example 2. A model car of mass m runs along a track and around a loop of radius 1.25 meters. Assume there's no air resistance or frictional retardation. The car starts with a speed of v meters per second. In part 1 we're asked, when it's gone round the loop by an angle of alpha degrees, what will its speed be in terms of v? Well, to solve this we need to use conservation of energy. Now if we use conservation of energy, we need to decide where the zero is for potential energy. So we'll take the lowest point, the flat road, as the zero potential energy. Then we have, when the car is at an angle alpha, we can find its height h by looking at the diagram. Now h is equal to AB, and AB is AC, which is 1.25, minus BC, which is equal to 1.25 cos alpha. So h is equal to 1.25 into 1 minus cos alpha. Now let the speed at angle alpha be u. Now we can use conservation of energy. The initial kinetic energy plus potential energy is equal to the final kinetic energy plus potential energy. Now the initial kinetic energy is a half mv squared, and the initial potential energy is 0. The final kinetic energy is a half mu squared, and the final potential energy is mg times the height, which is 1.25 into 1 minus cos alpha. Now we can cancel the m's, and we can multiply all the way through by 2. And that gives us v squared plus 0 equals u squared plus g times 2.5 into 1 minus cos alpha, or u squared equals v squared minus 2.5g into 1 minus cos alpha. And so our answer is u is equal to the square root of v squared minus 2.5g into 1 minus cos alpha. Now in part 2 we're asked, what speed will be needed at the top of the loop to ensure the car remains in contact with the track? Well, to solve this we need to mark the forces at the top of the loop. Now we've got two forces downwards. There's the weight, mg, and there's the normal reaction, n. We can see that for the car to remain in contact with the road, n must be greater or equal to 0. Now, if we resolve vertically down using F equals ma and a equals v squared over r, we have the force down mg plus n is equal to the mass times the acceleration, which is m times u squared over r. But we know n must be greater or equal to 0. Now that means mu squared over r has to be greater or equal to mg, or u squared over r has to be greater or equal to g. So u squared has to be greater or equal to rg, which means u is greater or equal to the square root of rg, which is the square root of 1.25 times 9.8, or the square root of 12.25, which is equal to 3.5. And so we have, for the car to remain in contact with the road at the top of the loop, u must be greater or equal to 3.5 meters per second. Now in part 3 we're asked, what is the minimum value of v, the initial speed, to ensure the car gets round the track? Well, the minimum speed for v is when u has a velocity of 3.5 meters per second and alpha is equal to 180 degrees. So, using the answer to part 1, we have 3.5 equals the square root of v squared minus 2.5g into 1 minus cos 180 degrees. Squaring both sides, that gives us 12.25 is equal to v squared minus 2.5g into 2. The cosine of 180 degrees is minus 1. So that gives us 12.25 is equal to v squared minus 49. So adding 49 to both sides, we get v squared equals 61.25, and if we take the square root, v is equal to 7.8262. So we have the minimum speed v to get round the track is 7.83 meters per second. In example 3, the diagram shows a particle of mass m starting at the highest point A on a smooth hemisphere having radius r. It starts to slide down the surface to a point B, making an angle theta with the horizontal. In part 1, we are asked to calculate in terms of r, m and theta the normal reaction between the particle and the hemisphere. Well, to solve this, we'll use the conservation of energy. Now, because the hemisphere is smooth, no energy will be lost. But we need to choose a zero height for the potential energy. So let the zero height be at the point O. Now let the speed of the particle at B be v. Then, using the conservation of energy, we have the initial potential energy plus kinetic energy equals the final potential energy plus kinetic energy. Now initially, the particle starts at a height r with no speed. So the initial energy is mgr plus 0. Now in the final energy, the height is r sine theta, and the speed is v. So the final energy is mgr sine theta plus a half mv squared. Now we can divide all the way through by m, and that gives us gr minus gr sine theta equals a half v squared. And if we double both sides, v squared equals 2gr into 1 minus sine theta. Now we can mark in the forces on the particle at B. There's the weight mg that acts vertically downwards, and the normal reaction which is in the direction of the line OB. Now if we resolve in the direction BO on the particle at B, using F equals ma, the component of the weight is mg cosine 90 minus theta. So we have mg cosine 90 minus theta minus n is equal to ma. But a is equal to v squared over r. And so mg sine theta minus n is equal to mv squared over r. Or n equals mg sine theta minus mv squared over r. But we've shown in equation 1 v squared is equal to 2gr into 1 minus sine theta. So we have n equals mg sine theta minus m into 2gr into 1 minus sine theta all over r. And in the fraction we can cancel the r's. So that leaves us with n equals mg into sine theta minus 2 into 1 minus sine theta. So n is equal to mg into sine theta plus 2 sine theta minus 2. So we get our answer, n is equal to mg into 3 sine theta minus 2. Now in part 2, we're asked to calculate the value of theta when the particle loses contact with the hemisphere. Now, at the point of separation, n is equal to 0. So that means mg into 3 sine theta minus 2 is equal to 0. And if we divide by mg, that leaves 3 sine theta is equal to 2. So sine theta is equal to 2/3, or theta is the inverse sine of 2/3. And if we work that out on a calculator, it comes to theta is 41.81 degrees. So the particle loses contact with the hemisphere when theta is equal to 41.8 degrees. In example 4, we're told a mass of 0.6 kilograms hangs on one end of a light inextensible string of length 3.5 meters. The other end is fixed. When the mass hangs vertically, it is given a horizontal velocity of 10 meters per second. If theta is the angle the string makes with the downward vertical, find the tension of the string when, in part 1, theta is equal to 0 degrees. Well, to solve this, we need to draw a diagram and mark in the forces. Well, the first force is the weight, which is 0.6 g acting vertically downwards. And then there's a tension in the string we can call T. There is no horizontal acceleration, so the only acceleration is vertical. We can call that A. Now we have A is equal to v squared over r, which is equal to 10 squared over 3.5 or 100 over 3.5. So resolving vertically using F equals ma, we have T minus 0.6 g equals 0.6a. In other words, T is equal to 0.6 times 9.8 plus 0.6 times 100 over 3.5, which works out T is 23.0228. So, the answer to the first part, the tension in the string, is 23.0 newtons. Now in the second part, we're asked to find the tension in the string when theta is 60 degrees. And again, we need to draw a diagram. Well, let the speed of the particle be u. Now we're going to use the conservation of energy to find the value of u. So we need to decide where zero potential energy is. Let's take it at the point A. In which case, the energy is a half mv squared plus mgh. Initially, when the particle starts at the bottom, we have the speed is 10 and the height is minus 3.5. So the initial energy is a half times 0.6 times 10 squared minus 0.6 times 9.8 times 3.5, which works out to be 9.42 joules. Now when the angle is 60 degrees, the speed is u and the height is 3.5 cos 60. So we have the final energy is equal to a half times 0.6 times u squared minus 0.6 times 9.8 times 3.5 cos 60. So the final energy is 0.3 u squared minus 10.29 joules. Now we know the final energy is equal to the initial energy, and that gives us 0.3 u squared minus 10.29 is equal to 9.42. In other words, u squared is equal to 9.42 plus 10.29 all over 0.3, which works out to be 65.7. Now if we go back to our diagram, we can mark in the forces. There's the weight acting downwards, and that is 0.6 g. There's also a tension in the string, and we can call that T. Now, let the radial acceleration be b. Now the angle between the weight and the direction of the string is 60 degrees. So resolving up the string using F equals ma, we have T minus 0.6 g cosine 60 equals the mass times the acceleration, which is 0.6 times b. But we know b is equal to u squared over r. So we have T minus 0.6 times 9.8 cosine 60 equals 0.6 u squared over r. Now we can replace u squared over r with 65.7 over 3.5. So T is equal to 0.6 times 65.7 over 3.5 plus 0.6 times 9.8 cosine 60. And that works out to be T is 14.2028. So the answer is the tension is 14.2 newtons. Now in part 3 of the question, we're asked to find the angle the string makes when it goes slack. Well, to solve this, again, we need to draw a diagram. To find the speed of the pendulum, we're going to use the conservation of energy. So, let the zero potential energy be at the hang point. Now initially, the pendulum has a speed of 10 meters per second and hangs 3.5 meters below the hang point. So the initial energy is a half times 0.6 times 10 squared minus 0.6 times 9.8 times 3.5, which works out to be 9.42 joules. Now when the string makes an angle theta, let the speed of the particle be v. Now its height will be 3.5 cosine theta below the hang point. So the final energy is a half times 0.6 v squared minus 0.6 times 9.8 times 3.5 cos theta, which is 0.3 v squared minus 20.58 cos theta. Now we know the final energy is equal to the initial energy. So 0.3 v squared minus 20.58 cos theta equals 9.42. Now if we divide all the way through by 0.3, we get v squared minus 68.6 cos theta equals 31.4, which can be rearranged. V squared is 31.4 plus 68.6 cos theta. We can call that equation 1. Now to calculate the tension in the string, we need to mark in the forces. There's a weight 0.6 g acting vertically down, and there's a tension in the string. We can call that T. Now resolving up the string, we can use F equals ma. Now the weight makes an angle of theta with the direction of the string, and so we have T minus 0.6 g cos theta equals 0.6 times the acceleration, which is v squared over 3.5. We can call that equation 2. Now if we substitute equation 1 in equation 2, we get T minus 0.6 g cosine theta equals 0.6 times v squared, which is 31.4 plus 68.6 cosine theta all over 3.5. Now at the point the string becomes slack, T will become 0. So we have minus 0.6 times 9.8 cosine theta equals 0.6 times 31.4 plus 68.6 cosine theta all over 3.5. So the 0.6 cancels. We can also multiply both sides by 3.5. So we have minus 3.5 times 9.8 cosine theta equals 31.4 plus 68.6 cosine theta. Now we can simplify that to minus 34.3 cosine theta minus 68.6 cosine theta equals 31.4, or minus 102.9 cosine theta equals 31.4, and so cosine theta is equal to minus 31.4 over 102.9. Now theta is the inverse cosine of that, and if we work it out on a calculator, that gives theta is 107.767. So the string becomes slack when theta is 107.8 degrees.